workshop. So we will have our second day of this marine data for Arctic Ocean, and this is a Copernicus Marine Service workshop. And today we will have the practical session. So yesterday we gave you an introduction to the Copernicus Marine Service and what sort of data you can find in the service and what we provide in terms of global data. And we also provided you some example on how you can use the data for Arctic issues. And today we will have a more practical session. So we will show you how you can visualize the data sets and how you can apply it to a case study. So before we start, we are going to go through some house rules and guidelines to help you follow this workshop in the best possible way. So first, please do not use the chat that you see on your right-hand side for your question. You can use it for small talk or to say hello to us. But if you have a more technical question or if you have any other question, we will use the Q&A section on the website. So on the top bar of your page, you will find the Q&A button, and you can click on it and you will find the area dedicated to the Q&A, and that's where you can ask our speakers your question today. And speaking of our speakers, so we will have 4 demonstrations for today. So we will start with the Copernicus Marine Toolbox presentation by Rezak that you saw yesterday. And then we will have the Jupiter and the QGIS tutorials presented by Alexandre Romerin from Noveltis. And finally, we will end with the Air Studio tutorial presented by Simon Millet from Noveltis also. So today, as I said, it's a practical session, so you might already have explored the tutorials that we made available for you on the website and the specific exercises that were developed for you today. So, So for the first demonstration, Rezak, whenever you want, you can start with the Copernicus Marine Toolbox.
Thank you, Gael. So good morning, everyone. I'm just going to share my screen to start. Okay. Can you guys see my screen?
Yes, it's okay.
Okay. So good morning, everyone. Hope you're doing fine. So for those who didn't attend yesterday's presentation, just a small presentation of myself. So I'm Rezak from Copernicus Marine User Support Team. And today I'm going to be presenting another main tool used by Copernicus Marine to browse and download data, which is of course the Copernicus Marine Toolbox. So as the name says, the toolbox is a free tool that allows you to browse and download Copernicus Marine data. It also allows you to get access to all the metadata and data sets from model, satellites, and in-situ observations. The tools also allows you to get specific information about the data sets and variables, and it also gives you access to download only subsets of these data. The tool can also be used to apply specific filters to download original data files as in the original form as they were produced. And when it comes to the memory size, as I said in yesterday's presentation, in case you are using the toolbox, the advantage is that you don't have a limit size when it comes to the memory. As long as your device can support the amount of data you are downloading, then you are good to go. Of course, the toolbox also allows you to download the data with high performance. This is due to the conversion of the data to the Analysis 3D Cloud optimized format, which is the ARCO format. Analysis 3D means that the data has been homogenized for easier use and interoperability. Cloud optimized means the state-of-the-art technology applied to optimally store the data, which allows faster parallel access to it. Various services are also provided within the toolbox. So we have the ARCO GeoSeries service, which is optimized to analyze data within a large geographical area within a small range of time. We also have the ARCO Time Series service, which is optimized for analyzing complete time series within small geographical areas. We also have the original files service, which allows you to retrieve and download the original data in the original form as they were produced by the producers. As it comes to functions, there is various functions that can be used within the toolbox. So we have the login function, which allows you to log in and get a file within your credentials in it. The advantage with this one is that it's a one-time process. You just need to be you just need to log in one time, and you won't have to do it again in case you want to download data repeatedly. We also have the describe function, which allows you to get information description about various dataset that you want to download. And with this one, you won't need to be logged in. We also have the get function, which allows you to get and download the original data files. And we have the subset function, which allows you to get only subset of datasets. So let's keep in mind that the get and the subset functions requires to be logged in to execute them, and unlike the describe function. To execute this function, you can use two different supports. So you have the command line interface. For that, you can use a Miniforce prompt, like in my case, or another terminal of your choice. Or you can use the Python API, application programming interface. For that, you can choose to use a Jupyter Notebook or a VS, a Visual Studio Code interpreter. So now let's show you how to get started with the toolbox. So as I said, to get started with the toolbox, just refer to the Help Center here and access to Help Center and FAQ. And then you will be getting various articles which speaks about various topics. And then the section you will need to access is the Copernicus Marine Data download. Just click on it. And here you can scroll down to get to the Copernicus Marine Data Toolbox section. So here you're going to get various articles which speaks about the toolbox and how to get started with it. So for example, here we have the introduction article, which basically defines the toolbox and how to use it with the main features in it. You can also refer to the main functionalities here that speaks about the various functions that can be applied within the toolbox in both the command line interface and the Python API. We also have, for those who don't wish to work with Python, the toolbox is also available in other languages such as R. And for that, you can just refer to the use cases section here. You can find various articles that speaks about how to use the toolbox in MATLAB, for example, or in R with use cases. At the end, we have troubleshooting and FAQs. So here we have troubleshoots article, which contains the most common issues that can occur during the downloading and installation process, and which can be very useful in case you are searching for answers for these issues. We have the FAQ article, which also contains the most common question asked by our community, reporting an issue or future request. This article tells you how to report an issue or a future request for development. And we also have next milestones and roadmap in here to track the past and future development. You can also refer to this icon here, to the message icon, to get a look at the latest version of the toolbox by going to the news icon and click on it. And here you can see that the latest version of the toolbox is the 1.3.4. Of course, as the user support team always recommend using the latest version to get the optimal experience when downloading your data. So yeah, and there is another way for you to take a look at the Copernicus toolbox in details. You can just click on the help icon here and type in your keyword, in this case, toolbox, and you will be getting various articles which speaks about the toolbox and the features that you can use within it. You can also message Blue, like I said in yesterday's presentation. You can ask him a question, let's say, for example, how to install the toolbox. So what Blue is going to do is going to explore all the information provided within the Help Center, and he will list the answer and give you the best suitable answer based on your request. At the end, he will give you there will be a source section which allows you to open a given article that could help you with that. Like I said here, the source section. So here is the Blue's answer, and then you have a source that can lead you to an article that could help you with that. In this case, the toolbox installation. If I click on it, and then I will be opening the article to install it. Speaking about installation, we always recommend using a Mamba environment. For that, it's really simple. First step to do is to download the Miniforce prompt or another terminal of your choice, and then follow the steps as shown here in this article to create your Mamba environment, and within it, install the toolbox. This process is really efficient. It allows you to set up your environment and install the latest version of the toolbox with all the needed dependencies. In this way, you will be sure to avoid all the potential bugs that can occur related to the deprecated packages. So it's a really efficient way. And now let's say that you have created your environment and you have installed the toolbox. You have followed all the necessary steps. So the next thing to do is to activate your environment. And for that, again, you can use two different support, either the command line interface or the Python API. So to start it, I'm just going to use my Miniforce prompt and open it like this. I don't know if you could see also my terminal that I opened.
No terminal.
Can you see the terminal?
No.
Okay, so again, I have to.
You can stop sharing and sharing
Yes,
again.
yes, that would be better. Okay, the terminal. So here I'm in my terminal. I don't know if you can see it now.
Yes, it's okay.
Great. So as I said here, I'm in my Miniforce prompt terminal. The first thing to do is to activate your environment, and for that, simply put this command, mamba activate Copernicus. Click on enter. So as you can see here, I'm no longer in my base, but in my Copernicus environment. Of course, Copernicus is the name I give to my environment. Feel free to give the name you want to yours. There is also a way to print your version of the toolbox. For that, you can simply put this command, Copernicus Marine, which is the name of the package, followed by the version option, like this, Copernicus Marine. Okay, click on enter. So here you're gonna get the version you are using, and for me, it's the latest one, which is the 1.3.4. Great. Now let's move on to the function that doesn't require to use the login function, which is the describe function. So if you want to print the information and the option that you can include within it, you can just click on Copernicus Marine, followed by the name of the function itself, in this case, describe, and add an option called help. Great. By the way, this one is used to retrieve information to get more information and description on the data you are interested in. And what this command gives you is that here you get access to all the options that you can include within your request. Of course, on the left, we have the options, and on the right, we have the description of these options. And I'm not going to dive in detail on each one. What I suggest is to refer to the articles in the Help Center. Just type in describe Copernicus Marine Toolbox, and you will be getting an article speaking about in detail about this one, how you can use it. Now let's move on to another function which allows us to get the original data, which is the get function. So just things up here, get the visualization. Great. So like I said, the get function, you can just again type in Copernicus Marine, the package. And yes, before I go to the get function, I will have to present the login. So the login function, which allows you to get your credential files, you will have to type Copernicus Marine login. So when running the login, it's going to ask for username. I'm going to put my username like this and my password. And when typing your password, just make sure to type the right one, because as you can see, you won't able to see what you are actually typing. So here it's telling me if I want to overwrite or not my credential file, because I already done the process. In this case, I'm gonna just click on yes just to show you how to do it. And now I have my credential file created. If I go to my default directory, Copernicus Marine, you can see that the file is created within my credentials in it. Great. Now let's move into the get function. To execute this one, we'll show Copernicus Marine get. Of course, if you want to again show the option that you can include within it, you can just add the help option here. And that will list you all the options that you can include also within your request. So only one is mandatory to include, which is the dataset ID. In case you want to download a given dataset, you have to join this argument. So you can just simply put dataset ID or I to short it. Of course, I'm going to give you an example to see how to use it. For that, I'm going to use the dataset I presented in yesterday's presentation with the uh, Copernicus Ocean Pro Viewer tool. I think I would have also to change my sharing of the screen to see how to use it. Okay, great. Going back to my yesterday's presentation. So for that, can you guys see my sharing? I mean my Ocean Pro tool.
Yes, it's okay.
Okay, great. So for that, I'm going to use, for those who didn't attend the presentation, you can see it, or you can refer to one of the articles. Just type in my Ocean Pro Viewer, and you will be getting all the info on how to use the tool. And now I'm going to the download icon here and original files, browse files, just to copy the name of my dataset. More easy this way. And now let's run my command, Copernicus Marine get, and followed by the I option, like I said, with the name of the dataset. Of course, I'm not going to download the entire dataset because it's too large. Now I'm again in my terminal. I don't know if you can see it.
It's okay.
Okay. So like I said, I'm not going to download all the data sets because it's too large, but I can specify filters to download only certain area. For that, I can simply use the regex option by clicking on filter and followed by this syntax. So let's say I want to download data from the 22nd to 23rd March 2024. It is simple, just click on 2024, the month March, from open brackets here, 22nd to 23rd, close the brackets, and close the syntax like this. So this will allow me to get the data files from March 22nd to 24th. And I can also add another option to specify my output directory. For that, you can just add the O option. Of course, to see more in details about this option, just type help, and you will be getting all the info on how to use it within the function. For that, I'm just going to copy the name of my output directory to copy the path. Okay. Just make sure to type in the right syntax here. I think we are ready to download it. Click on enter. So here it's going to list us some info on the dataset that I've chosen. Of course, here the version was not specified, so it automatically takes the latest one. Same thing for the part, it automatically takes the first by default, and other option info also on the dataset that I have chosen. In here, it's telling me the size of the data I'm downloading, and here it's asking me if I want to proceed with download or not. Of course, I'm going to say yes. And now the data will be downloaded. And if we go to the output directory, we can see that the data is being downloaded. I just have to show you the output directory that I've used to store my data. So here, data, you can see that the data is being downloaded. Now let's move on to, so of course, I'm just going to abort the downloading process because it will take some time. And now I will present the next function, which is the subset function. And for that, I'm going to use a VS Code interpreter. It will be more easy this way to present how to use it. I think I have also to change the sharing. Okay. Now I'm in my VS Code editor. So first thing to do is also to activate your environment. For that, you can just go here to the kernel section and select the proper environment, in my case, Copernicus. The next step is to import the package. Just type this command, import Copernicus Marine. Run the cell. After that, I'm going to use a similar command to type to get more information about the subset function. And for that, you can just use the name of the package, Copernicus Marine, followed by the name of the function, subset. At the end, you just have to put an interrogation point like this, and you will be able to print all the options that you can use within this one. As you can see, there is also various options that you can use. I will give an example to use this one. Same thing, going back to my presentation of yesterday and show you how you can download it. Okay, so here I'm in my Ocean Viewer Pro interface. And for that, let's say that I want to download a certain area. Again, this what I'm about to do, I've already presented it in yesterday's presentation. So you just have to rewatch the presentation. You will be able to see the process. Here, if I click on define on map, I will be able to select a certain area like this. So let's say this area, and as you can see, the information are automatically filled. And let's say that I want to download data from the 5th June 2022 to the, let's say, the 6th of June 2022. Just click here, go back to the window as in map, 6th of June 2022. And as you can see, the process went pretty easy this time because yesterday I wasn't really able to type in the right date. Of course, such things could happen. All you need to do is just refresh your window and that will do the work. So here I have all the info. What I need to do now is go to the automate section here, click on it, and I will be getting two different templates. So if I was using the command line interface, this is the one that I need to copy. In this case, I'm using a Python API, so I just have to switch to the Python API template and simply copy it and go back to my VS Code editor. So here in my VS Code editor, I'm just going to paste it simply like that. And as you can see, the import of the package is included, but I don't need to repeat it. So just delete this one. And now we can also add another option to specify the output directory. For that, just specify the path to my output directory. Again, just copy the path here, go back to VS Code, paste it. And there is also another option I want to talk to you about, which is the force download option. Make it to true. So this one basically allows you to directly download your data without being asked if you want to proceed with the downloading or not, unlike we have seen it in the command line interface. So let's run the cell and see it. So now, as you can see, again, printing some info on the subset I've chosen, and then proceeding with download. And now my data is downloaded. And if we go back to my default directory, we can see that the data is indeed downloaded right here. So now let's move on to the next function, which is the open dataset function. For that, again, if you want to print more info about this one, you can just type Copernicus Marine, open dataset, the name of the function, followed by an interrogation point, run the cell, and as you can see here, the different options that you can include in it. And to give you an example, I will just copy this piece of code because it's basically the same thing. I just have to change the name of the function. So like this, change the name. And just for this one, the difference between this one and the subset is that in case of the open dataset function, you cannot include the downloading process because simply they are not included here. So basically, the open dataset allows you to only remotely open your data and manipulate it as you like. There is also a way to save the subset that you have opened, which I'm going to present just in a few seconds. So, but the main difference is that the downloading option cannot be included with this one. So here I'm just going to set this to dataset and print it, run the cell, and you'll be able to see all the details I have selected here in my subset. All right, so as we can see here, I have the dimension, the coordinates, also the variable I have selected, which is the CI thickness. And like I said, there is a way to save this subset by using a method which is called the toNetCDF method to save your data in netcdf format. For that, you just have to type dataset point to netcdf, which is the method, and again specify your output directory. Copy the path to my directory, followed by the name of the output file. In this case, I will give it the name of data.netcdf, and now run the cell. Great. Now, if we go back to my output directory, we can see that the data is indeed downloaded in a netcdf format here, data.netcdf. So going back to VS Code, and now I'm going to present another function, which is also similar to the open dataset one. So I'm just going to copy this piece of code here. This one is called read data frame. So the main difference between the read data frame and the open dataset function is that in this one is used to open the data in data frames, as the name says. And in case, it's also interesting in case you want to visualize your data in the CSV format. And just a small info about this one, the data is no longer available in Xarray packages, but in Pandas. And in case you want to open the data, just make sure to create first your subset of the data and then open it. Otherwise, you can get a message telling you that the data you have selected, the amount of data you have selected is too large to be displayed. So let's see if we can display this subset that I have selected with the read data frame function. For that, just run the cell and we're supposed to get the data opened in data frame. Awesome. So as you can see, I have here my CI thickness variable along with my dimensions in data frame. So as I said here, with this one, it's pretty interesting, that useful, because you can open this data and visualize it in CSV format. And for that, there is also a method. And to do this one, I'm just going to copy this command because it's basically the same syntax. Just change here to netcdf and use the to net CSV method. And here, of course, you have to change the format of the file because I want to save them in a CSV format. Run the cell. And if we go back again to our directory, we'll be able to see that the data is indeed saved in a CSV format like this.
Okay, Zach,
Yes?
you're starting to go a little over time. If you could go faster or just conclude whatever you want.
Okay. Yes, I am basically finished. So yeah.
Okay.
Okay, so yeah, I already arrived at the end of the presentation. So just to close things up again, if you need to get started with the toolbox, just refer to the articles in the Help Center. And there is also an important information. Not all the datasets are available to use within the toolbox. To take a look at the changes, just refer to the user notification service here. Scroll down to datasets availability on new services, and then you will be getting a PDF table telling you on how to the datasets availability to be downloaded with the toolbox, and the one that are in progress to that. And again, if you need further assistance, just contact Blue or join us as the user support team. Will be glad to answer your questions. I hope you enjoyed this presentation, and if you have questions, ask them. I will be glad to answer. Thanks again.
Thanks a lot for your presentation. So yeah, we have a few questions for you.
Okay.
So the first question is, so in the open dataset function, can I eventually open a portion of my data if needed using different dates and or coordinates?
Yes, it is possible to open your dataset function. This is basically what the function is used for, is that it allows you to open different parts of the datasets based on what you need and the variables that you need by selecting the variable that you need and also the coordinates. And if you want to select certain area, yes, it's possible to use it for that. You can take a look. There is an article speaking about the open dataset in details. You can take a look at it in the Help Center, and yes, you will be getting more info on that.
Okay, thanks. We will try to put the link of the article in the chat, but thanks for the explanation. So this question is why you use Mamba to use the Copernicus toolbox.
So it's not mandatory to use Mamba, but we recommend using it because when creating the Mamba, you are sure that you can prevent the issue related to the deprecated packages, because sometimes during the downloading or the browsing or downloading your data, you can have bugs related to deprecated packages. And this is why we recommend using Mamba, because it allows you to install the latest version of the toolbox and within it all the related dependencies. So yeah, Mamba is the one that we recommend.
Okay, thanks a lot. This question on the open data frame function works too when you have data in isGrid.
So for this one, I'm not sure if I can give you the answer right now, but you can join me the question and I will see into it in details, and then I will give the best answer to it in the question and answer section.
Okay, yeah, so
yes,
yeah,
yes.
we put the question aside
Yes.
for the post-event report, no problem. Okay, two more questions. So the first one, is there a difference between Copernicus over dataset and ARI open dataset?
Copernicus over dataset. I think
it's
it's
the function
open,
from the
open dataset. Okay, open dataset and array open dataset. I don't know if there is an array open dataset function. Again, put the question inside to the side. I will see it in details, and perhaps I can give you an answer for that.
Yeah, I think it's, from what I understand, if the option, the function open and over
Yes, it
dataset.
speaks about yes, it's about the open dataset, but array open dataset, I don't really have an idea right now, an answer to give. So yeah, let's put it aside, and I will give the answer later on.
Yeah, no, you can say. Okay, next question. So not sure if it's relevant, but is it possible to make a CIS loss map directly on the command line?
I don't think that we can do that. I want to make a CI slots. I will try to see it also in details, because this one also requires some of searching in the help center. I will try to see if I can come up with an answer for that too. I don't know if it is possible to do that in the command line.
Okay.
So yeah.
Okay. Yeah, I will also put it on the side. No worries. Okay, we have time for what? Oh, sorry, we have time for one more question, and then we will move on to the next presentation. Is there a way to find the dataset ID straight from the toolbox without going to the home page?
I think not. You will have to go through the data store to find your dataset. Of course, first you have to select your product, and within your product you have to go and search for your dataset, and this is where you can find your dataset ID. The toolbox cannot give you the direct access to your dataset ID. It's just a way for you to download this dataset.
Okay. Okay, great. Okay, so we will move on to the Jupyter Notebook presentation. So thanks, Rizak. You have a few questions aside to answer for the post-event report, but thanks for your presentation in the Q&A section.
Thank you.
And okay, so Alexandre, whenever you want, the floor is yours for the Jupyter tutorial.
Thank you, Gaël. So hi, everyone. I'm Alexandre Brun from Noveltis. So I'm going to share my screen to present you the Jupyter Notebook. So right now you should be able to see my screen. Is it visible?
Yes, it's okay, we see it.
Okay, perfect. So I'm going to present you with this Jupyter Notebook a little case study on the Arctic Ocean. So this will be focused on the Arctic sea ice, so which is a strong regulator of the Earth's climate, and it's also an important feature for the local ecosystems and also human activities. And of course, as you know, recent observations have shown that the sea ice extent has been decreasing over the last decades, especially in summer, which is a time where it reaches its minimum. And so this has a lot of impacts on the climate, on the ecosystems, especially in the region, and of course on the sea level, sorry. And so I'm going to show you a little case study about that. So we're going to use sea ice data and temperature data and see how it all correlates and what are the impacts of the melting of sea ice. So of course, we'll be using Python for this tutorial. Here's a brief overview of the different libraries that we're going to use in Python. So if you already use Python, you should be familiar with most of them. So NumPy is a classic library for scientific computing. Pandas is commonly used to process tables of data. And Xarray is mostly used to process NetCDF, which is the most used format for scientific data. And finally, we use additional libraries like SciPy for some statistical computing, Matplotlib and Cartopy to draw maps. And datetime is useful to process time series. So I'm not going to execute everything because we have little time, but this is the cell where we import all the libraries. And now I'm going just to show you what data we're going to use for this tutorial. So we're going to use a product from the Copernicus Marine Surface Catalog, which is called Arctic Ocean Physics Reanalysis. So it's a reanalysis based on the model with assimilated observations, which has a 12.5 kilometer resolution. And with this, we have daily, monthly, and yearly data from 1991 to well, almost today, December 9, 2023. So this is a great time coverage because when studying trends for climate data, we usually want to have several decades of data. So this is why this dataset is particularly interesting. So if you're already using this notebook, if you want to know more about the dataset, don't hesitate to visit the homepage of the product, where you have a complete description of it, how to access the data. And here you will see all the different physical variables that are available. So in our case, we'll be using so the sea ice thickness, the sea ice area fraction, and we'll also use the seawater temperature, which is here. So to access the data, I'm using the Copernicus Marine Service Toolbox that have just been presented in the previous presentation. So I don't think I need to go again over how to use the subset function. But as you can see here, this is the ID of the dataset that I'm using. So I retrieved it from the home page here. Here are the two variable names that I want to retrieve. So sea ice thickness and sea ice concentration. I will retrieve temperature in the next cell. Here is the area of interest that I want to study. Here is the time range that I want to study. So I'm taking 30 years of data. So from January 1991 to December 2021. I'm choosing a depth range that actually only yields the surface level for these variables because we don't have different depth level for these variables. And here is just the output path and file name for the data. And I'm doing the same thing here for the temperature. So here I'm doing this on a different cell because this time I will want to have temperature over several depth level of data. And if I don't want to have a too big a data set, I have to do this separately. And after I've executed these cells, my data is here. So this is just duplicate, but this is temperature and this is the sea ice concentration and thickness. Okay, so in the previous presentation, you've also already shown how to open a NetCDF with Xarray and how the variables are displayed here when you open a dataset with Python. So here I've opened the sea ice dataset, and you can see that we have the sea ice concentration here. You can have more details on the variable here. So more precisely, sea ice concentration is actually the sea ice area fraction, which means that for each pixel of data, this is the proportion of the pixel that is covered with ice. So it goes from 0 to 1. And we have our 3 dimensions here, so latitude and longitude, of course, and our time range. So we have chosen monthly data, and we have dates, so January, February, March, up to 2021 December. So the next section is about drawing a simple map with Python. So to do this, you first have to select an area of interest. So here, of course, we are selecting the high latitude. And this is a cell to draw a map. So of course, we have to select a single date to have data in 2 dimensions, only latitude and longitude. So here we're plotting a map of the sea ice thickness in this September 2021. So as it sometimes takes quite some time to plot the data, especially in North Polar stereo projection, I'm doing this to coarsen the dataset to have bigger pixels and therefore less data to plot, and so it takes less time. And we're using the North Polar stereo projection to have a map centered around the North Pole. So here, here is an example of the sea ice area thickness, sea ice thickness in September 2021 in meters. And you can see that from once you reach lower latitudes, the sea ice thickness is 0 because there is no more sea ice, especially September, where the sea ice is near to its minimum. So in the next section, we'll be interested in the sea ice extent trends. Sorry, as I said before, we have a sea ice concentration variable that accounts for the fraction of each pixel covered by ice. And here we want to compute the actual sea ice extent in square kilometers. Which is something that is not necessarily trivial because, as you can see here, as you go to the higher latitudes, the pixels here get smaller and smaller because of the projection system. So we have to be precise when we compute the total area of each pixel, which is what we are doing here. So based on the latitude and longitude values on the radius of the Earth and so therefore on the so we were computing the cosinus between the latitudes, angles, and and the radius of the Earth to have the total length of the different total side lengths of the side of the pixels. So this takes some time, but with this cell, we compute the total area in square meters of each pixel. And now we only have to multiply this variable by the sea ice concentration to obtain the sea ice extent in square kilometers or meters. I don't think I've already done the conversion in this cell. And so this is our sea ice extent variable that we'll be using in the next sections. So now that we have processed this and obtained our sea ice extent variable, what we want to do now is to study the trends in the evolution of the sea ice extent over the last 30 years. So to do this, first of all, we can remove the seasonal effect because, of course, it reaches its maximum in winter and minimum in summer. So we want to have only the yearly trend of the data. So with Xarray, we can use the resample function, and using this argument to resample and obtain yearly values. And then using the SciPy function line regress, we can compute the slope and intercept, but our main iterate is the slope because it is actually the trend in the data. So if we process this, we obtain those values here with a strong correlation coefficient. But only seeing those values is not very well. We can't really know what it represents, so we are going to plot the data along with the trend to see how the sea ice extent has evolved over the last 30 years. And as you can see here, those are the yearly values of the sea ice extent in square kilometers over the last 30 years. So we can see that it is decreasing. And in green, this is the trend line of the data. And apparently, so the sea ice, the Arctic sea ice is decreasing by apparently 46,000 square kilometers per year. And but here we have computed, this is not necessarily the most significant trend because we have computed the sea ice data and trends over a complete year. But as I've said in the introduction, the most dramatic changes happen during summer. So we're going to do the same calculations, but this time only selecting winter and summer to see if there is a difference in dynamics between those two seasons. So to do this, we use the cell function of X-array, which allows us to select only the month of February, so month number 2 in the dataset, and the month of August for the summer in the sea ice dataset. We perform the same calculations both times, and we obtained the sea ice trends for winter and summer. And you can see that during summer, here on the right, the trend is decreasing almost 3 times as fast as during winter. So this is 66,000 square kilometers per year of decreasing, and this is only 24,000. So that we can see the difference in dynamics between summer and winter. So now in this section, we will see how the trends are distributed spatially. So basically, we're going to do exactly the same calculation before each pixel of the data. And when we do this, we can see that there are areas where the sea ice is decreasing a lot more than others. So without surprise, it's mostly around the edges of the sea ice in the lower latitudes. And we have a few here hotspots here where each pixel is losing around 30% of sea ice fraction per decade. And a few spots here where it is, on the contrary, increasing, but this is really marginal compared to the overall dynamic. So now we're going to use our temperature dataset that we have also downloaded. So the difference here that you can see is that this time we have 4 dimensions: latitude, longitude, time, and depth, because we have temperature for several layers of the ocean. So you can see that we have 16 depth levels for this, and our depth level go from 0 to 100 meters. So in this first section, we're going to quickly see the correlation between so the evolution of the sea ice extent and the associated temperature at the same dates. So this is what we do in those cells. It didn't exactly work the way I intended, but we have the graph that we expect. So as we can see here, we have temperature versus Arctic sea ice in a million square kilometers. And as we can see, the two are strongly correlated. We have almost, we can clearly see some sort of line here that goes through the data. We have a strong correlation coefficient of almost -1, which accounts for a strong inverse correlation. So the more temperature, the less the sea ice extent. And we can also see, okay, I get what didn't work. It's the color bar that's not displaying here. Okay, it's fixed. So as you can see here, the points are colored by a year. And as you can see, where the sea ice is maximum here, we only have the bluest points. And even for winter month, the recent data points are still show that the sea ice is smaller than the older points. And for summer, it's the same thing. The highest temperature and lowest Arctic sea ice extent values are almost all belong to very recent years here, because we have points that are almost all pink. And finally, in the final section, we will look at one of the impacts of the sea ice melting, which is the change in the ocean heat content. So this time we only look at the temperature dataset. So as you probably know, the sea ice has an impact on something called the albedo effect of the Earth. Because when the ocean is covered by ice, the sunlight is reflected by the ice, but if it's not, the sunlight is absorbed by the ocean. And this causes dramatic differences in temperature in several depth layer of the ocean. So what we will do here is we'll select a slice of the ocean and see how the temperature within those deep layers evolves with time. So here we're selecting our slice. So we'll show you on the map right afterwards. So we'll be looking at the data in this slice. So we're going to compute the temperature as a function of depth and as a function of longitude. We're only fixing the latitude level. And if we choose a date, for example, here, August 2021, we can see that we have a strong temperature as a first, but a temperature that's also diffusing here in the deeper layers. And this is probably a consequence of the absence of sea ice in this area. And now we're going to look at the evolution of this area over the last 30 years. So we're going to select all the months of August of the last 30 years and compute the same graph and gather them all into an animation. So this will take some time to execute, so I should already have my my outputs saved, yes. So I can only show you the animation. So as you can see here, our color palette is always the same, but in this area over the most older years, we have a very few years that have a strong penetration of temperature in the deep layers of the ocean here. But as we go into the more recent years, we can see that the years where we have deep penetration of temperature are more and more frequent, which is caused by the absence of sea ice and the absence of albedo effect. Okay, so if you do the notebook at home, you have a few exercises that you can do. So studying other areas, studying other variables. So feel free to do that. And we are reaching the end of this tutorial. So if you have any question, feel free to ask me anything. I hope you enjoy this presentation. Thank you.
Thanks a lot, Alexandre, for your presentation. We have a few questions about the tutorial. So for the general question about the use of the tutorial, if you want to run it on the Jupyter Hub, you need to have an account and be registered to the Copernicus Marine Data. And then you can find the tutorial on the public folder, and you need to move it to your home directory. You can also download the tutorial on your computer and run it yourself on your Jupyter Notebook on your own computer. But yeah, so for the Q&A, okay. So the first question, is there a tutorial like this for working with forecast data? So I guess we can use your tutorial with other data, if I'm not mistaken.
Yes, there are very similar data sets that provide with forecast data. So I think, yes, with a few perhaps modifications, this should work. But I think there may be also other resources on the Copernicus website of the many tutorials that we've done over the years.
Yeah, there is a whole catalog of Jupyter notebooks and other tutorials, so you can have a look and search by keyword if you want. Okay, this one, I have an addition. Can you do a 3D scatter plot with any other variable in your live presentation script? So maybe it would take a little bit of time, but yeah.
Yeah, it should be possible.
But yeah, you can also add a cell directly into your notebook if people want to add something to it, obviously. This question, what is the radiative transfer model behind the depth weight data?
Reanalysis, I guess.
Yeah, reanalysis data.
I think it's written in the
project
notebook product. Yeah, I don't have the name. Yes, Topaz system.
Okay.
So I don't know what model they use exactly for the radiative transfer, but if you look more into the user manual and quality information document, you may find the information you need. I haven't investigated that myself, so.
Yeah, but yeah, with the name of the product, you can find the name of the model, so it's not an issue. So this general question, will the scripts be available post-course activity? So actually the tutorials are already available on the website. On the top bar of the event page, you can find the Jupyter Notebook, RStudio, and QGIS tutorial, and you can download the tutorial there with the data, the scripts, and everything. There is also a 1-hour video to explain everything to you step by step. And just one question. Will there be information about displaying rotated coordinates? Arctic data is often in those rotated coordinates that are a bit tricky to display with Cartopy.
I'm not sure what you mean by rotated coordinates.
If it's the polar coordinate.
Yeah, if it's the polar, because most of the data used is in, a classical coordinate system. So latitude, longitude from -180 to 180, and from, I don't know, I haven't worked with any other coordinate system. What is tricky with Cartopy is using this projection because it causes, it slows down the plotting process a lot. Which is why I said in the presentation that I had to coarsen the dataset just for the plotting, because otherwise it takes too much time to plot in this projection. But this is the only problem I've encountered when making this tutorial. So yeah, I agree. Sometimes it is tricky to work with for us in this projection with Cartopy, but well, the only solution I found is to lighten the dataset a little bit just for the plot. So.
Okay, thanks a lot. So that was the last technical question about the tutorial. So thank you very much for the presentation. And so we will see everyone again after the 10-minute break, and we will have Alexandre doing the QGIS tutorial and Simon the RStudio tutorial. So see you everyone in 10 minutes, and feel free to chat with each other in the chat or grab a tea or a coffee, and see you. Welcome back, everyone. I hope you had time to take a little break. We will go to the QGIS presentation of the tutorial. So again, Alexandre, welcome back, and whenever you want, you can start the tutorial presentation.
Yes, thank you, Gaël. So hello, it's me again, Alexandre Romain. So this time I'm going to present to you another use case on QGIS. So let me share my screen and we'll be able to start. So this time we're going to still look at CI's data. Sorry, I'm just going to set up a little slide for the introduction. It will be prettier. So here we're going to still study the Arctic sea ice. So if you follow the Python tutorial, you will be familiar with some of the data that we're going to use. This time we'll look at the impact of the melting on the marine ecosystems. So we'll be going to look more at marine wildlife data, so plankton, and also we'll look at polar bear localizations. So let's get into it. So here I'm starting on an empty QGIS project. So I've already preloaded some data, but this is just in case of I'm going to show you how to load all of this. So first of all, when you start a QGIS project, what you want to do is to load a background layer, so a base map basically. So here you have to go to the browser on the left and select the XYZ tiles, one of the base map that is available. So if at your stage you don't have anything on this folder here, you have to right click and type the new connection. And here you can set up a base map and retrieve it from the web. So on the user manual of this tutorial, you will have an example of how to retrieve the Google satellite background layer, which is the one we're going to use. So now, as we are going to look at data on the Arctic sea ice, we want to change the projection system of QGIS. So here you can go on the bottom right-hand corner and select a new projection system. So you can, here for me, it's already in my history of system that I've used. But here you can select the EPSG 3995. So you can just research it and select it here. It's going to take some time to load, but we are going to have our North Pole Center QGIS in a few seconds. Okay. So now we're going to load our first data sets. So it's the same product that we've used in the Python tutorial, so the Arctic Ocean Physics reanalysis, I mean, for this first section. So this time we're going to plot the sea ice concentration and the temperature. And so to plot data from the Copernicus Marine Service catalog, you have to use a QGIS plugin, which is, sorry, there is a tutorial in the user manual on where to download it on the website and how to install it from the downloaded zip file. So I'm not going to show it because we don't have much time. And once it's installed, you can select the import NetDF plugin. I'm going to delete all of this. And now you can add NetCDF data to QGIS. So I'm just going to show you an example on how to do this, but it's already all preloaded here, but as for the demonstration. So here is the data that we've prepared for you for this tutorial on this use case. So all you have to do is to select the netcdf data and drag and drop the files in the plugin. Oops, sorry, it's disappeared. So we have here with the physical here PHY letters, this is our physical data. And we have our temperature and sea ice concentration data. And so if you want to load it into QGIS, you can right click on one of the variables, add layers of several variables. Here we have data from 2007, 2014, 2021. Let's choose here, for example, we are working with, sorry, 2021, okay. Let's select sea ice concentration temperature data here. You can see that we have monthly here data sets. Select all of them. So this is the temperature. Don't forget to type in that it is from 2021 because we are using several years of data. And if you do add, close, and you do the same thing for sea ice concentration, it's already all selected. And you can see that our data is loaded in QGIS. So they're all loading at different times, so it's why it looks animated. And so here on the upper layers, we have our temperature, and you can deselect the data sets progressively to see the evolution here of temperature. So here is June, July, August, etc. So I'm just going, as I've already loaded the dataset, I'm going to remove them because it's overloading my QGIS files. And so I don't really know what's happening here. Okay. Sorry, it just seems that I've mistakenly deleted the CI, sorry, the temperature data from 2021. So just going to reload it quickly. Add layers, CI concentration, 2021, and we should be good to go. All right. So now I'm going to show you how to style this layer to have a more consistent view of the data. So to just change the style of a layer, you just need to go to Properties. It will open you this window, and now select Symbology. So this is a raster data with a single band, so you can choose a single band pseudo color. And here you select the lower and upper bounds of the data. So here is the CIS concentration, so the fraction of each pixel covered by ice. So it goes from 0 to 1. And here we can choose our color palette. So we'll choose blue for sea ice. And when there is zero sea ice, we want to have a dark blue because there is no ice. So you can click on this and invert the color ramp. And if you apply this, click OK, you should see a change. And now you can see the Arctic sea ice here here it's February 2021. And you can apply the same thing over the other dataset. And to go quickly, you can right click on the dataset that you've just styled, copy the style, and apply this on all the data on all the group of layers. So paste style. So it's taking some time to load. And here, as you can see, take some time, but all the dataset should have the same color. And of course, you can do the same thing for the CIS concentration in 2027, in 2007, 2014. And you can do the same thing for the temperature here. But here you will do this with a different palette. So symbology. So this time we'll go from -2 degrees Celsius to 18. Select the spectral palette. And once again, we want to have blue for low temperature. So we'll invert the color ramp, classify, copy the style, and paste it. And now if we compare sea ice and temperature on the same date, we will see that there is a strong correlation between the sea ice extent and the temperature. So for instance, here, if we select only the month of September in 2014, so let's just deselect everything except September, the one that had a 0.9 here. So this is the sea ice in September. And if we go for a temperature of 2014 and deselect everything, you can see here that the sea ice is only located in the low temperatures. So this makes it quite obvious. Okay, so next thing I'm going to do now is to do a quantitative classification of the sea ice layers. So we will only be looking at the September data because it will be easier. So I'm just going to show you one example, and then I've already preloaded everything, so you won't need to we won't need to do this everything live. So what we do here is that we are going to change this raster data into vector data. So you have to use your processing toolbox, or you choose here in vector geoprocessing tools. And for this one, we want to, in raster conversion polygonize, raster to vector. We are selecting the sea ice concentration layer from 2014 September. So I'm trying to find out where it is. Sea ice concentration 0109 2014. We want to change the name of the new variable that we're going to create to sea ice concentration. And if we run this, we obtain this big vector layer. So this covers all the area of the raster product that we have just visualized. But now that it is a vector, we can filter it. So as you can see, we have now the sea ice concentration variable that we have downloaded. And if we want to only visualize the area where that are fully covered by ice, we have to select the sea ice concentration that is equal to 1, because it means that the concerned pixels is fully covered by ice. And if we do this, only this remains. And you can see that it is still consistent with the temperature pattern that there is under it. Okay, so I've already preloaded this for the several years of data here. Oops, sorry. And filtered it for all the years. So this in green, this is the one from 2014 that I've just shown you. In orange, under it, this is from 2007, and on top of it, this is from 2021. And sorry, And the final thing that you can do is to compute the area of each of the sea ice layers here. Oops, sorry. So this is quite simple actually. So let's take, for example, 2014 here. So what you have to do is to toggle here the editing mode. So now the layer can be edited. And now you can open the field calculator. With this calculator, you can create a new field. So we'll call it area in square kilometers. Let's say we want a decimal number. And here is the expression to calculate the area. And with vector data, there is an expression that directly calculates the area of a polygon that you're using. So this is just using this symbol area, it will detect the area, and we are multiplying it by 10 power minus 6 to have it in square kilometers. So I've done this. You can re-toggle the editing mode to save your changes. And now if I open here the attribute table of this layer, here is what I've just calculated, the area in square kilometers. So I had already done it before and saved the product, so it's already appearing, but this is what I've just done in this lesson. Okay, so this section was about calculating the square area in square kilometers of the sea ice layer. Now we are going to look at zooplankton data. So we are going to move to the marine wildlife part of the training. So to load this, you have to do exactly the same thing as before with the plugin from used to compute to load the Copernicus data. So this time we are using the Copernicus Marine Service biogeochemical reanalysis. So it's a different data set. If you want to know more, there is a link in the user manual, but this is the homepage of the product. And this time we'll be using we'll be looking at the zooplankton concentration here. So in millimole per cubic meters. And here we've only loaded for the month of September. Take some time to load. And just like before, you can style differently the layer. So using the symbology window, we go for a concentration of 0 to 15 millimoles per square meters, cubic meters, sorry. And applying this, copying it and pasting it to the other years, we have the zooplankton concentration in this region, so with higher values in the lower latitudes. So here, this layer is from 2007. Oops, sorry, I've erased the background layer. And if we look at the sea ice at the same period, we have something that is that quite resembles the sea ice extent that we have just computed before, especially in this area. And so what we're going to do now is I'm going to show you how to sample data at several locations of the dataset. So to do this, it's quite simple. So all you have to do is go to the layer tab, say create layer, new shapefile layer, because we're going to draw points in on the dataset. So you can name the file anything you want. Here, for instance, I'm going to, sorry, I don't know where to save it. Up. I'm just going to save it here. As the geometry type, I'm going to select points. And we should be good to go now. So here I have an empty point layer, and now we're going to toggle the editing mode again and select this to add points to the dataset. And so we want to sample data of the rasters, for example, here. So ideally, this is point number 1. Here, this is point number 2, or here, this is point number 3. And we can save our data, and we have our 3 points here. Now we're going, if we look at our points, we only have the IDs of the points. We want to add the geometry attributes to have longitude and latitude attributes on the point layer. So we're going to use this function from the processing toolbox. We have selected our point layer. And if we run this, we have a new point layer here. So you can rename your layer with, for example, points with geom. And here, if we look at the table, we have coordinates. So in this case, they're called X and Y. This is obviously longitudes and latitudes. And now we can sample values from the zooplankton data from those points. So basically, you can also use the processing toolbox and choose sample raster values. So here we've selected our points, not pints, with geometries. And we can choose the raster layer that we want to sample. So here we want to sample our zooplankton here. For instance, let's go for the 2007 data set and run this. And now if we look at the output of the data, you can see that on the sample 1 column, we have the zooplankton values under those points. And so you can generalize this strategy. So I'm just going to change the style of the points to have to see them more clearly. So we have our 3 points, and now in the table we know what are the from 2007 the zooplankton concentration values over those points. And you can also generalize this strategy on any area of interest that you have. And you can also repeat this operation on the other years of data. But in order to save time, I'm going to go to the next section right now. So now that we have looked at the zooplankton data, but let's look at bigger animals, for example, polar bears. So we retrieve polar bear data. Oops, sorry, I've misclicked on the data, which is available here on the dataset of this training in this folder in the form of a CSV file. So I'm going to show you how to import this into QGIS. So what you have to do is select the layer tab, select add layer. Sorry, I've misclicked on the wrong option, and select add delimited text layer. So this is the window that opens. And now you have our file explorer, your file explorer with the CSV file, and you can just drag and drop it in the file name tab here. And now you can just set it up before importing it to QGIS. So here, if you just select CSV format, it should detect well the format of your file and Here you have a sample of the data and you can check that it is correct. So I can see that we have a table that seems valid with the fields here that are correctly represented. And you also make sure that the X field and Y field are filled with longitude and latitude, which are those two attributes. So once this is ready, you can add the data to QGIS. And you can see here that we have our polar bear observations here that have just been added. So we can see this, but this is already a little bit chaotic. So what the first thing we can do is to color the points according to each individual bear that is classified in this data set. So you can go to symbology, choose categorized, on the value choose bear. And if you classify this, you will have as many colors as there are bears classified in the data. So we have more than 60 bears here. And you can see that there are already some individual trajectories that you can be distinguished, but it's still a little chaotic. So we're going to clean the data set and select only the observations on periods that we are interested in. So first of all, we're going to erase the potential duplicates in the data. So delete duplicate geometries. You choose this in the processing toolbox. I'm going to rename the dataset to have a better view. Oops, sorry. Made a little typing mistake. So we've lost the style that I just set up, but it's no worries because you can just copy and paste it from the previous layer. Paste style. Okay. And now we're going to filter the data to select only the time periods that we have sea ice constellation data for. So on this dataset, we're going to choose 2007 and 2014. So when you open the filter window, you can build here your query. So here I want to have year, I want it to be equal to 2007 or to be equal to 2014, because this is the years of the data that we have just studied. And I want to have the month of September. If we click OK like this, we can see that we have only a few bears remaining now. Okay, so I've just been informed that I should conclude very soon because I'm going over time. Okay, so it's okay because we are mostly finished. So here we can see that we have individual bears and their trajectories. One thing we can do with point data, one thing you can do now is to split the data to have one file per bear. So you can just split the vector layer, use this based on the bear attribute. I hope it worked. If it didn't, it doesn't seem to have worked. Bon. So it doesn't seem to be working. I'm just going to use the data that I've already prepared to show you and conclude. So basically, for example, what I wanted to show you is that you can compute the trajectory of a single bear here using and changing the points into a line. And the last thing you can do is to calculate the length of the line to compute the distance well, that the bear has walked. And you can compute this for all of these trajectories. So I'm going over time. So if you want, you can do that by yourself by following the user manual of this tutorial. So I hope you will be able to make it, but it's not too difficult. So you should be able to compute all of this. And we are reaching the end of this tutorial. And well, I hope you also enjoyed it. So thank you very much for your attention.
Thank you very much for your presentation, Alexandre. So we have a few questions for you. That's why we stopped you. So the first question was this one. So for new user of QGIS, is there a list somewhere that has the digit code numbers to search for the right projection in the filter? Someone in the chat talked about the EPSG website. I don't know if you know about this one.
Yes, this is usually where I go to research when I want a specific projection. It's usually very convenient here because it gives you the EPSG code and you just have to type this in QGIS and it will yield the necessary projection that you want for your project. So,
okay. So this one is about the vertical line across the pole in the polar projection. Is it a singularity in the visualization? It's only because of the projection, I
think it's only because of projection and of how the background layer is set up. So I don't think all of the background layers are affected by this. But yes, the Google satellite background is so.
Okay, thanks. This question, can the Copernicus Marine Service QGIS plugin be used in the QGIS graphical modeler to automate all the steps presented and further process the downloaded data?
I don't think this is possible. At least I haven't heard of this possibility before. So to be honest, I don't think that this functionality is supported by the plugin.
I will put it on the side and ask the user support. Maybe they know the answer. Thanks. Okay, next question. Have the polar bear observations been collected using EO or other traditional sampling techniques?
I'm not sure about how the polar bear has been collected. I think it's a very diverse data because it goes from 1985 to 2015. Okay. So I think that several different techniques have been used to do this. From what I've read, so it's been collected from satellite link transmitters.
Okay.
So I don't know how they've done it exactly, but yeah, I think that depending on the time period it's been collected, it might differ from one bear to another.
Okay, thanks a lot. Okay, this one, how can I smooth the spatial resolution and how can I change legend of an existing netcdf file in QGIS?
So for the legend, I think with the symbology window, you have already a lot of options. If by legend you mean only changing the colors, I don't think there is too much trouble with QGIS. Perhaps what you mean is you want to change here the values displayed. Not sure that you can do this with raster products. For vector data, it's quite easy. You can easily here change the legend here, for example. But for rasters, I'm not sure that it is possible.
Okay, thanks. So the next question, general question, using QGIS, R or Python is a matter of preference, but is there an actual advantage in using one or the other tools in terms of performance? I guess it depends what you want to do with the data you use.
Yes, I would definitely use Python or R for processing very big data sets. And for example, for copying time series, but in setups where you want to have a quick and dynamic visualization, QGIS is definitely the way to go. But of course, it is not convenient to process big data sets because you need a lot of memory to handle them.
Yeah, definitely. Next question, also a general question. Could polar bear tracking data have applications in submarine navigation or marine research? So I think you could use the way you track polar bear data to track submarine navigation, but I don't think polar bear data could have application in submarine navigation. But for marine research, yeah. Okay. So for the next question, in some datasets, some cells, probably due to cloudiness, appears as NA. What is the best way to fill these gaps? I think interpolation is fine now.
That's what I would do also, yeah.
Yeah. Yes, when you miss data, interpolation is the best way to not miss data anymore, actually. Okay.
As long as the holes are not too big, but
yeah, definitely. Yeah. Okay, so that was the last question for the QGO. For the QGIS. So thank you, Alexandre, for your 2 tutorials and the Q&A session.
Thank you so much.
We will go to the RStudio tutorial presentation. So Simon, whenever you want to, you can start sharing your screen.
Yes, thank you. I will share my screen. So, hello everyone. My name is Simon Millet. I'm a scientific engineer at Novartis in France, and I will be your trainer during this session in air. You will use a Jupyter notebook to see acidification sea in Arctic. We will have a closer look of CMM's product, their structures, format, variables, and how to explore and plot them. A notebook is composed on different cells, and some of them has a code on it. So after exploring the netdef file, we will make a basic plot, then a comparison between different variables, then a creation of animation, and finally we will see the evolution of pH over the years. As you may know, the Arctic covers a vast area. Most of it is being inhabited, but human activity have a significant impact in the Arctic. The increasing level of carbon dioxide, CO2, in the atmosphere, which then dissolve in the ocean, cause acidification of the Arctic Sea. This process is particular concern in the Arctic for several reasons. First, because cold water absorbs more CO2 than warm water, which accelerate the acidification. And then with melting sea ice leads to greater mixing of fresh water with seawater and changing ocean chemistry and accelerate acidification. The acidification has impact on marine organisms, particularly marine organisms with built bare shells or skeleton from calcium carbonate, such as mollusk, coral, and plankton. And change in the population of plankton and other organisms affect higher species, such as fish, seabird, or marine mammals. And Arctic acidification is critical environment because it threatens local ecosystem and population that depend on. So in this training, we will see the pH, over the months and years and over parameters such as plankton. So first, the air environment. So for this training, we will it is necessary to have these libraries. So RNetCDF, that is an interface for NetCDF file format. ggplot2 is a system to create plot and graphics. dplyr is a library to manipulating data. rColorBrowers is a library for colors colors in plot. NetCDF4 is an interface for NetCDF file format. GridExtra is a library for arranging a multi-plot. Lubridate is a library for fast and user-friendly analysis of that time. And Magic, it is used for the animation. So first, we will load the different library. If it is not installed in your environment, it is possible to install with this command, install a Pond package and all the necessary libraries. So today we will work with the Arctic Ocean Biogeochemistry Analysis and Forecast. We will find this dataset in the Copernicus Marine Data Store. You have the link here. The data is already downloading in this training, that is in the data here. And this is the characteristic of data. If you want, we can try to download this data, but we will need have your own Copernicus Marine credential, username and password. So first, we define the path of a NetCDF file, and then open the dataset. There is a edge variable, for example, chlorophyll, the mass concentration of chlorophyll in sea water, and you have all other variable. Here you have 4 dimensions. You have depth. The size is 1 because we have downloaded only the surface. There is latitude, longitude, and time. And here it is a global attribute to have more information about the dataset. So here we load all variable, and then we will visualize, for example, one variable, the zooplankton. We see here we print the dimension. We see the longitude, latitude, and time, and then we see the values of zooplankton for the first longitude, the first latitude, and the second time, because in R the index begin in 1, contrary to Python that is 0. And we can visualize also the variable of time, but we see it is a number, it is not a date. So to convert the number to date, we use these cells with function as point posings. We put the time and the origin. The origin is done in the characteristic of the variable time. Here you see it is a second since January 1970. And we see that it is now a date. So first we will make a basic plot. Donc first we determine the figure size. Then we create a data frame that is the input for the plot. We can see the first 20 values of the data frame, and then this cell create the plot and save in folder figure here. So we see the pH. So it indicates the acidification of Arctic Sea along the Greenland coast. So it is just for one date, but we will see more variable in the next section to see the comparison between the variable. So in this part, we will compare, we first create a plot function. So it is the same plot here, but it is a function that is simplify the code for the next. So here we create, so the function name is mapping. So in this cell, we create a plot for the variable SpCO2, that is the pressure of CO2 in surface. And we plot P2, that is the variable pH. And then we plot the two plot, and we see the two maps for the same date. We see that there is a great similarity between the two maps. Here the pressure of CO2, and here the pH. We see where when PCO2 okay. So we see the two map. Here it is the pressure of CO2, and here the pH. So when the pressure increase, for example, in the west of Greenland, we see that pH is lower, so it is more acid. So now we see the similarity between the pressure and the pH, and we will see the evolution with phytoplankton and zooplankton. So we do the same thing here. And we plot the four maps, so the pressure, the pH, zooplankton variable, and phytoplankton. So we'll see the same two maps for the pressure and pH. And here it is the zooplankton and phytoplankton. We see here where the pressure is important, and so pH is low. There is less zooplankton, but with phytoplankton there is no trend because ocean acidification have benefit some species of phytoplankton, but harm other. So it is for this we don't see a trend. But for zooplankton, there is many zooplankton species who are vulnerable to lower pH, which could reduce their population and affect food availability for higher animals. So now we will create animation to see the evolution of these 4 parameters over the years. So we will create an animation only for September. With this sale, we define 0.9 for September, but we can try with other months. And then here it is a cell to can create a whole plot, but it take some time, and so we have already done in this folder here, and we plot the animation here. So we see that the pH is different over the years for September. And thanks to this animation, we see the evolution of the 4 parameters over the years. But with the map, we see the general evolution, but it is difficult to see if acidification increase over the year or not. So in this part, we will see the evolution of pH over the years. So we will take an average of pH in the entire map. So over the whole data here, and we will allow us to have a global vision of the evolution of pH and not on the specific point. So this sale for each year do an average annual mean of each point, and after we do the average over the years for the whole point. So here you see the value. So we see the 2 first years there is no change, but after we see a decrease of pH, so an acidification along Greenland. So to see in graph, it is we see that there is a decrease of pH and therefore an acidification of Arctic Sea or in Greenland. Even if the variation is small, because the maximum is 8.0.5 and the minimum is 8.0.3, there is a strong impact on biodiversity. And moreover, the increase in chemical pollution in Arctic due to mining, wall or marine transport is one of the factors behind that increase the CO2 and toxic product that increase the acidification of the Arctic. So continued ocean acidification in this region has considerable consequence on marine food, particularly affecting organisms at the base of the food chain, such as zooplankton and phytoplankton. So the training is now finished. Thank you for your attention. I hope you enjoying this presentation, and if you have a question, do not hesitate.
Thank you very much, Simon, for your presentation. Sorry about the little technical issue in the middle,
Yeah.
but it should be okay now. So we had a few questions on the Q&A session. The first one was about how to download Siemens data using directly R. So I guess I think there is a R packages to do that.
I don't know. I download directly with the Copernicus Marine Data Store, and then put in my Jupyter lab.
Okay. So I will put the question aside, but yeah, I think there is a R package on Copernicus to do that also. So I have this question also. I asked to have a little bit more context about it because I'm not sure I understand it, but I guess the person was wondering if Memba can help with the environment for the R tutorial.
I think no, because Mamba is for Python, and so for R is not useful.
Yeah. Okay. Okay. So for the question, okay. So still an open question about is there a reason for using Jupyter rather than RStudio?
Yes, because for presentation is more useful to use Jupyter, but it is the same code for RStudio.
Yeah, you can also find the RStudio tutorial in the Jupyter Hub in the right environment if you want to use it like that. But okay, so that was it for the question for your presentation. We had lots of comments on the chat saying it was a nice presentation also. So